IB is a diagonal matrix. As you all know, a moment of inertia matrix, by choosing proper coordinate system, you can diagonalize it. Let us say I1, I2, I3 is 0, and let us assume I1 greater than I2 greater than I3. All right. So, remember the equations were this way. Okay. This has to be 0, right. So, we have omega 1 components of this cross zero. So, now tell me what are the equilibria. So, this means it is so what are the equilibria? Yourself. All zeros, omega 1 0, omega 2 0, omega 3 0. Does everybody agree with that? That is one equal. Is that the only equilibria? Okay, call it, we are calling it omega 1, no? Yeah. These are the states. So, 1 equilibria, okay, let us write it here. Do you see that? We have 3 sets of equilibria. Corresponds to spinning about the smallest inertial axis, spinning about the largest inertial axis, spinning about the intermediate axis. Now, this is a common experiment. If you throw a tennis racket up, right, it preferentially orients itself in a certain way and spins, right, which basically shows that one of the moment of inertia axis is unstable. So, it moves to the stable axis of rotation, and that is what the Euler equations will show you. Now, how do we compute? So, these are equilibria, which is saying that you are actually spinning. You are spinning about axis 3, but it is still an equilibria, right, of these equations. Now, which of these equilibria are stable, which are not stable, which is what we will see tomorrow. We will prove the stability of these equilibria. So, I will stop here for today. If there are any questions on what we did today or what is the any other interpretations, I will be happy to answer, otherwise we can stop. Yes. So, yesterday I think we left at just the equilibria of the rigid body, the spinning rigid body. So, the equations we had were omega dot and for equilibria so for the equilibria analysis we assumed I was with and we had the equations as omega 1 dot let us give some names. So, I think you had I2 minus I3 omega 2 omega 3, right? Is that right? Can you tell me the first?
Yes, I3 minus I2 omega 2 omega 3 I1 minus I3 omega 1 omega 2 I2 minus I1 omega 1 omega 2.
Is that correct? All right. So, let us call I3 minus I2 as A1, okay. A2 as I3 minus I1 and A3 as I2 minus I1. Okay. So, let us rewrite these equations. So, that is omega 1 dot omega 1 omega 2, right. And now we were talking of equilibria of the following form. All right. So let's look at this first one. So what does this first one means? It's spinning about the smallest, the largest axis. Omega 3 is not equal to 0. So how would I find out if that equilibria is stable or not? What I would do is, these are a nonlinear system. One way of doing it, which we have not really presented yesterday, is look at the linearization of the system about that equilibria and see if the eigenvalues of that linear system or the A matrix lie in the open left half plane, right. So that means stability. So let's do that. So what is the linearization of the system? So this system is now linearization about an equilibria means, so X equilibria, so the A matrix would be this evaluated at x equals x naught, correct? Has everybody seen this anywhere before? How does this come about? So just to give a simple explanation of this, so you have an expansion of x as x equilibria plus some deviation, right. So now if I use that here, right. So what does this become? This becomes this, right, because this goes to 0. And if I expand this about in a Taylor series expansion about x equilibria, this symbol is the same as this, plus this means higher order terms, right. So this here is my A, this is equal to 0, it is an equilibrium, that is my A matrix, clear, right. So let us find out what the A matrix of this is. So can you tell me what A, and for this let us look at 0, 0, 1, just call this 1, some constant value, right. So what is, so first and foremost let us get df at any x. So what would that be? That would be this partial with omega 1, 0 partial with omega 2, which is a1 omega 3 partial with omega 3 minus okay. Now we have to evaluate this at this equilibrium. Please stop me if you are not clear about what I am doing. So evaluated at, let me call this equilibrium 1. So that is 0, 0, 1. So now what are the eigenvalues of this matrix? Can you please compute this, eigenvalues of that? Does that look okay? What are the lambdas? Oh, sorry, I'm sorry, I forgot this. Right? Lambda I minus A. Determinant of lambda I minus A equals 0, right? Please remember, the way I have chosen I1, I2, I3, each of these constants is positive. What are the eigenvalues? All three zeros? Lambda squared, lambda cube. Is this the equation? Is this correct? The equation? So what does that mean? So that implies correct? So this unfortunately leaves this test inconclusive, because what happened, all the eigenvalues were on the imaginary axis. 0 is on the imaginary axis, the other two are on the imaginary axis. So when you perform linearization of a nonlinear system around an equilibria, and the linearized system has eigenvalues on the imaginary axis, then your test for stability is inconclusive. You need to resort to something more, one of which is called the center manifold theorem, which we will not study here, and there are other techniques. So I will not go into how what is the other technique we use to determine the stability of this? So, there is another technique called the energy Casimir technique. So, I will not go into those because I think that will kill time for my other main theme of today, which is introducing you to smooth manifolds, right. So, let us leave this here, but using those techniques one can show that. So, let me write okay. So, I will not go into those, but now why do not you examine number 3 yourself? Now, you will find, why do not you examine number 3 using the same analysis? Can I request you to do that? Find the eigenvalues associated with equilibria about the intermediate axis. What is the A matrix? All 3 zeros? No, is it 0 0? What else? Yeah. Then? So, what are the eigenvalues? Plus minus A1 A3. Well, in this case one root is on the right half side, so you can immediately conclude it is unstable. So, as I mentioned yesterday, the equilibrium about the intermediate axis is an unstable equilibrium, but the equilibrium about the smallest and the largest axis is stable, but we have not proved it here simply because we need extra techniques to do so. You cannot do so from such linearization arguments. So, I think that will stop my okay, I think maybe I will show you a nice picture of why see at the beginning of our lectures yesterday, we saw something called phase portraits, where we drew how a simple harmonic oscillator, how it evolves. Those diagrams, if you remember those ellipses, etc., those are called phase portraits, which basically show the evolution of a dynamical system from any initial condition, how it moves. So, now I will just connect the laptop for a few minutes before I get on to my next, because so that will give you an idea of what is happening. Next part of these lectures, which is understanding what a smooth manifold is. So, we won't go into a very rigorous definition of what this is, but we will try to give you the essential tools so that you can understand some of the recent problems being done in control in using geometric techniques. So, when you see something like rotation in SO3, you should not feel, oh, what is this? I mean, you should be able to relate to that. Okay, all right. So, let us first take some examples. So, let's take the plane or R2. Let us take R2 and let us take the unit circle, right. Let us take the unit circle. So, this has okay, all right. Now, this unit circle, I will give it a special symbol, I will call it S1, right. If there was a unit sphere in 3-dimensional space, I would call it S2. So, S1 is sitting in R2. It is a subset. S1 is just this, is a subset of R2. Similarly, S2 is a subset of R3, the 2-dimensional sphere sitting in 3-dimensional space, and you can go on. S3. So, what would S3 be? S3 would be defined as all those 4 tuples in R3 such that to 1, right. Same way here you started with x1 squared plus x2 squared equals 1, right. Okay. Now, let's look at this object and let us maybe consider some point here. Let us consider a point there and take a small portion of this object around that point. I have just taken a small portion of the circle. So, let me enlarge that. So, I have taken, right. It is open. So, these last endpoints are not included, right. Okay. And now, let me define a few things. Let me define a function. So, now I will do the following. This is the circle, and let me call so this enclosed region, right, I will call an open set in R2. Please notice this is like around here and it contains that arc of the circle, right. And I will define the following. I will define a function u is now this R2 as -1, right. Now let me evaluate the Jacobian of this function, right, at some particular value of x1, x2, call it alpha beta, right. Can you tell me what this Jacobian is? So let us say alpha beta was some point here. All right, it does not have to be there, it has does not have to be on that green circle. What is the Jacobian of f? Two x1, correct, 2x2 evaluated at alpha beta, right. So that is 2 alpha 2 beta, correct, right, indeed. Now if I asked you the question, so remember this, call this sum, it is a constant matrix, right, it is a 1 row 2 column matrix. Is A an onto matrix? How many of you know what is an onto and how many do not know what is onto? You do not know what is onto. So onto means, so let's take A. What does A do? A takes some region U which is sitting in R2. Is the purple clear? Can I request people to come ahead please, because it makes it easier for me also, so that I do not have to write too big. First 3 rows, because there are only few, if people who are beyond the 4th row, can you come ahead? There are many seats in front. So we will try to just keep first 3 or 4 rows, that should be better. And can you maybe come over instead of the corner? I mean, there are many seats here. Yeah, there are also 2 seats vacant here. There are okay. Okay, so A is a mapping from U, this A. Is a mapping from U to R1. So when I ask the question, is A an onto mapping, or is A an onto matrix or mapping? right. What I mean is, if I am given any real number, right. So, let's write A. So, A takes some two vectors, say psi, eta, and gives you some answer, right, correct, right. Now, if I give you any real number, can you find a psi and eta? So, let us say any real number means gamma, right, let us say gamma. So, can you find a psi and eta to give you gamma? If I specify any gamma, can you give me a psi and eta to give me, so that this gives you gamma? Is that true for this matrix? Then if it is true, it is called an onto matrix or an onto mapping. Yes or no? Yes or no? Or let's yeah, depends on, okay, yeah, that's a good answer. I mean, depends on the value of alpha beta. Let's take alpha beta are non-zero, right, being that region. Say let's not. Let's say alpha is say something like, let's take it as 0.5 and 0.5 or something like that. Okay. So, if alpha is 0.5, this is 0.5. So, we are talking of 1 1. Right. Yes, whatever gamma you give me, I can always find a psi and eta to give you that gamma. Therefore, for this particular matrix, the matrix is called onto. It is called an onto matrix or an onto mapping. When do you think, for which values of alpha and beta do you think this will not be an onto matrix? 0 0. Suppose one of them is 0. No, it will still be onto. Even if one of them is 0, it will still be onto, because you can always play with one of these, right. Okay. So, the only case where it will not be onto is when both are 0, right. Okay. So, that is an onto mapping, right. So, now let us erase this. Okay, so now, so these I'm sort of moving towards properties which will help me establish that the circle is what is called a smooth manifold in R2. This is my objective, right. So, first and foremost, I have been talking of something called an onto mapping. Onto mapping from U to R, and this mapping was of this quantity df at any point alpha beta in this U. Okay, it is onto. Now, there is another property of f. Okay, well, next let us go to another question. So, the number 2 or another issue is There are quantities called level sets of functions. So, what does the level set of a function mean? That if I have a function f from some m variables to r, and this is a smooth function, so everything is differentiable many times, then the sets of the following form: where C is some constant, right, are called level sets of this function f, right. We will also put the condition that this gradient of this f, right, oh r, sorry, f to r not rn, okay. So, now why do I bring in this notion of a level set, right? Because I would like to insist that this onto function, this function was onto in this interval, that this green portion of my circle, this was just this part, this green portion of my circle can be written as the level set of this function. That means, in other words, that green portion of your circle is f is all points, so the green portion, so let us call it the green portion equals all points in R2 such that f x1 x2 equals 0. For instance, if I evaluate x1 squared plus x2 squared minus 1 here, will it be 0? No, it will not be. It will be 0 only on this line, on this arc of the circle. So, the arc of the circle is a level set of this function that I have defined. So, I have two notions which I have introduced. One is an onto mapping, and this is onto at every point here. So, therefore, we will give it a new name later, and second is the portion of the circle we are interested in can be expressed as the level set of this function. Are these two things clear? Then I will proceed. Okay. So, now I will write two things. One is f is onto in U, in that whole U. Therefore, it is called a submersion. This is a new word, submersion on U, right. And second is S1 intersection U. That is, I take the whole of S1, intersect it with U, I will get this portion of the circle. S1 intersection U is a level set of F. If I satisfy, if I am given an object in Rn or R any Euclidean space, right? In this case I was given a circle. If I can check whether those two conditions are true for every small portion of that object, that is, what I need is, say around this point I chose a small portion of the circle, I found an open set in the outer space which is R2 found. So, this portion of the circle was U intersection S1, right, and I could find a function which was onto everywhere here, and this portion of the circle was a level set of F. Two important properties. Function 3, function should be smooth. X1 squared plus x2 squared minus 1 is a smooth function. Take the partial derivatives, they are all continuous and differentiable, right. Now, second is that in the region U, the onto property holds. 3 is that portion of the object you are examining is the level set of a level set of that function, right. If these are satisfied for every point, you can find such an F and such a U, then that object is called a smooth manifold in that outer space. So, in this case I will conclude, or a smooth submanifold, it is like a subspace in a larger vector space. So, this is a smooth manifold in R2, right. Let us take, I started with the circle, which is a fairly nice example to start with. You can do the same thing with a sphere sitting in R3, do the same thing. Now, the open sets will be what? If you take a sphere and take a point on it, an open set will be like a ball sitting in R3. You will have to find a function and the onto requirement, everything. You can take a similar extension, then your function will become x1 squared plus x2 squared plus x3 squared minus 1. Do the same thing, right. Now, let us take a more unconventional example, or rather something which is different. And I want you to try it now. Let us take, so example 2. Any questions? Somebody had a question? No? Okay, I will call smooth manifolds by M. So, this is all matrices in 2 by 2 matrices such that so my question is M a smooth manifold? What is the larger set here? It is all the 2 by 2 matrices with real numbers. Now, I am considering a particular subset. Earlier what did I do? I took the whole of R2 and then I considered a circle which was defined as all those points which satisfy x1 squared plus x2 squared minus 1 equals 0. And I established that the circle had those two properties I was looking at. Now, my set from earlier R2 is now my bigger set is 2 by 2 matrices. I am taking a subset which is all such matrices which satisfy this property. Basically, they are all orthogonal matrices, right. So, I want to ask the question, is the set of all orthogonal matrices sitting in R 2 by 2 or 2 by 2 orthogonal matrices, is that a smooth manifold? So, can you check the two conditions and tell me what the function should be? Exactly the same thing. Try. I will give you 2-3 minutes, just try, then I will show you the solution. Can I erase this? Everybody is taken. So, these are the, I will call it O2, orthogonal 2 by 2, this thing, okay, sitting inside this, all right. So, let me take a small region just like I took in the circle, right. So, now I will again bound that by some u. Please look at the parallel to the circle, bounded by some u, right. What is my objective? To find those functions which should have the onto property on u, and then establish this portion of this as a level set of those functions, right. So, now first, so let us go back. Suppose I characterize my 2 by 2 matrices as x1, x2, x3, x4. What will that lead?
Can I treat the matrices as x1, 0 and 0, x2? If I take this, my function would be x1 square plus x2 square minus 1, the same problem.
But why do you want to reduce the set of matrices? Set of orthogonal matrices is much larger. Why should it just be x1, 0, 0, x2? That is a smaller set. Okay, so A transpose A is identity means this. So, therefore, that means x1 squared plus x3 squared is 1, right? Then x1 x2 plus x3 x1 x2 plus x3 x4 is 0. Then x2 squared plus x4 squared is 1. Does everybody see this? So I will call f1x as x1 squared plus x3 squared minus 1, f2x as x1 x2 plus x3 x4 . As opposed to the circle, what is different here? In the circle you had just one function. Now I seem to have landed up with 3 functions. The circle you had x1 squared plus x2 squared minus 1 was the function, and that equal to 0 was the circle. Correct? Now I seem to have 3 functions. Now if each of these satisfies equals 0, then the matrix is orthogonal. Right? x1, x2, x3, x4 is just any matrix. But if each of these is 0, then that matrix is an orthogonal matrix, because it satisfies these 3 conditions. Correct? Okay. So now, can you tell me what is the first condition I was looking for in your previous definition? Now, to give you a clue, I will consider the function. Remember, it was u, so now this u is from 2. Earlier case it was to r, but in this case I have 3 functions r3, and this f I will define as f1 3 functions. And what was the first thing we checked last time? That it should be onto at every point in U. It should be onto. Now, how do we check onto here? Okay, one thing probably I did not make clear was when we checked onto, we checked the onto property using the Jacobian of the function. Please remember, that's important, the Jacobian of the function, right? So, yes, in fact, we wanted, so I think probably I made a slight mistake when I defined things. When I show the slides, maybe I will correct that. So, the function has this property of a submersion, means its Jacobian is onto in that region at every point, the df. So, what is the Jacobian here? First and foremost, what will be the dimension of this Jacobian matrix? 3 cross 4. Why 3 cross 4? This is from, there are 4, right? So, this will be dou f1 by dou x1, dou f1 by dou x2, dou f1 by dou x3, dou f1 by dou x4. 3 by 4. Clear? So, can you give me the Jacobian? Now what is meant if in, so this again let us come to our figure. This was a small sitting in 2 by 2 matrices was the orthogonal matrices. In that I took a small patch, just like I took that small portion of the circle. That small patch I covered it with some open set of R2 by 2. Now I want to establish the properties of this function in this open set. That clear, right? Now I want to ensure that the rank of this matrix evaluated at any point here is, what should its rank be if it's on 2? 3, perfect, because this is mapping to R3. So if I give you any number in R3, this, so let's take it at, just as before, let's take it at some point alpha, beta, gamma, delta. So what will this be? Correct? So how will you establish that this is on 2 in this region? Can you tell me? I think you have done a little bit of smooth manifolds. Yes? No? Okay. So how will you establish that this mapping is on 2? Let's do the following. Instead of trying to look at any point here, let's in fact take the point in the set of orthogonal matrices, right? So what conclusions can we draw? When will the rank of this drop to 2? When 2 of the rows are linearly dependent, right? So when will it drop to 2? Okay, any two of those become 0. In fact, you are right, because if you look, this matrix will not be, or that's not true. That's I don't think correct. See, alpha, beta, gamma, delta is like this, right? X1, right? If this becomes 1, 0, 0, 1, still orthogonal. 3 of them should be 0, okay? Or, well, if this becomes 0, this becomes 0, it's no longer orthogonal. It's 1, 0, 1, 0 is not allowed. Because then the rank of the matrix is 1. A transpose A is no longer identity. Please see that clearly. See, this is fine. This is in orthogonal. This is not in orthogonal because it doesn't satisfy A transpose A equals I. Right? So this is okay. Is that clear? Okay. So, in fact, if this is an orthogonal matrix, you can go ahead and show that this is rank 3. And the reason you can show that this is true close as well is because this function of x, that Jacobian cannot change so abruptly that it loses rank immediately, because these are all smooth functions and we are evaluating this matrix at the Jacobian at a value. So, if it is true close by, so if I take a close enough neighborhood, then the rank will still be 3. Do you see that argument? Because the functions are smooth, it is like this. These are the orthogonal functions. Now, I am evaluating the Jacobian at this point here. Now, I take a very close neighborhood of this. The Jacobian cannot suddenly lose rank because the functions are smooth. So, that is the logic of the argument. Okay? I will not go into more details of this, but let us check the next condition, that portion, that pink portion should be the level set of these smooth functions, and that is anybody, I mean, leaving the last part of this argument, which was a little bit sketchy, is the essence of what we are doing followed. Please tell me if it is not clear. Okay. Right. So, indeed, this here is the level set of this function f, because it is all points for which, so level sets are also written as this S, or that patch is all x right, because this is equal to 0, this is equal to 0, this is equal to 0 is giving me all the orthogonal matrices. So, we could conclude at the end of this exercise that the set of 2 by 2 orthogonal matrices sitting in the larger space of 2 by 2 matrices forms a smooth manifold. Okay, so now if we were to go on, the most important matrices that we look at as aerospace, mechanical and probably electrical engineers in the context of electromechanical systems is the special orthogonal matrices in the 3 dimensions and the special Euclidean matrices. So, I will explain what those are. Proceed. the second one, the first one is a smooth manifold sitting in 3 by 3 real matrices with that property, which is basically all the rotation matrices. The second one is called the special Euclidean group, which is basically the matrices which will explain rigid body motion, translation plus rotation. So, the P term there, which is in R3, shows the translation of the center of mass, and then the A is just a rotation matrix. So, any rigid body you have translation plus a rotation. So, I think we can stop here. This will be a logical conclusion for this. Let me see, it is 11:20. I will stop here, and I will probably show, I will transfer, I will transfer. Should I show it now or next?
I'll see if tea is ready.
Yeah, sure, Can see it? Okay. Okay, so this is a graphic of what happens rigid body motion when you have spin about certain axis. So, here we have actually drawn the, I do not know whether I explained that aspect, okay, maybe I did not. So, these are the body momentum axes. So, pi 1, pi 2, pi 3. Now, what this figure is showing is, if you look at the rigid body motion, the equations that the motion that the Euler equations describe, there are two conserved quantities there. The two conserved quantities, one are kinetic energy and the other is the spatial momentum, because there is no other gravitational field or any other potential field which sort of changes the momentum. So, if you plot the momentum, so the momentum vector being a constant can be translated into a sphere of the momentum. So, that is basically a vector x1, x2, x3 and a vector in R3, right. If that is a constant, so its norm, or you can say x1 squared plus x2 squared plus x3 squared is also a constant, right. So, that is being plotted as a sphere. Now, if you look at the kinetic energy expression, so maybe I should have put that down, I will do that after I finish this. The kinetic energy gives rise to ellipses here. So, this intersection, that these flow lines that you see are the result of ellipses like this, or ellipsoids, not ellipses, ellipsoids intersecting the sphere, right. Whether ellipsoid like this, depending on what type of a sort of initial condition and what is the level of energy that you are on. So, now let us observe two things. Look at, so this is the smallest inertia axis. So, if you get perturbed here, you will stay circling close to this. You recall Lyapunov stability, right? You stay circling close to this. Now, come to the intermediate axis. The intermediate axis, if you get perturbed slightly, look at the way these flow lines are. One approaches here, from here, here, but this diverges. So, the minute you get perturbed, you just move either here or you move here. Whereas, now again come to the smallest inertia axis. Look at the flow lines, the phase portraits, they just are circles here. So, if you get perturbed here, you keep doing this, which is what, this is a graphical interpretation of why the intermediate axis is unstable. These flow lines show that, and these flow lines are obtained by intersecting the momentum sphere with the kinetic energy ellipsoids. So, those are ellipsoids, this is a sphere, and the intersection forms these flow lines, right. So I've given you an explanation of how you can get the stability results which we left incomplete for the two stable cases using something called a Casimir. The little bit about Lyapunov functions that we taught you, maybe you can try to understand these two slides or these three slides, and this is the conclusion. And this is what we did for the intermediate axis instability that we showed. Okay, so this is not important. Yeah, so this is some basic linear algebra. Okay, maybe it's nice to go through this for, okay. Differentiable smooth functions help us to characterize derivative maps. So, the rank of an n by n matrix definition, the rank of the Jacobian, right, is referred to as the rank of F. So, this was the point I made use of in the second result on 2 by 2 orthogonal matrices. Since F is smooth, all the functions are differentiable many times, and the value of the determinant is a continuous function of its entries, the rank remains constant in some neighborhood of X. So, if you get an orthogonal matrix close to that, the rank will not change. I did not talk about diffeomorphism, so do not worry about them. This term I have used. So, if you have a mapping from an m-dimensional Euclidean space to an n-dimensional Euclidean space, again smoothness emphasized, if the Jacobian is onto for all p, then F is called a submersion, right. Oh, I am sorry, I think there are some comments made. One of my students had asked for corrections. So, how do I shut this off? Do you know how to remove them? I mean, while is there some, what's the, I just click there?
Comment option is there.
Where is, oh, learn. Oh, but I can't get it full screen again.
I think it will not go like this. Control.
Oh no, but again it, okay, anyway, let us not worry about it too much. So, this, please, I will modify these slides when I send them to you. Do not worry about three equivalent definitions. I have taught you smooth manifolds, essentially this, I have used this definition. Do not worry of these two, just use this definition. Now, let us run through these. Unit circle, okay, you do not need this, you just need the first. Remember, I said just use the first definition, these are all equivalent. We did this. Okay, I think that's all we need from here. Okay, now coming to why do we need smooth manifolds? We need smooth manifolds because objects like rotations are not like Rn, right? They are not vector spaces. When you learn linear systems, you are doing x dot equals Ax plus Bu, where x at any time is in Rn. Rn has different properties than the smooth manifolds, the most simple being that you can add two vectors in Rn, right, and what the result you get is in Rn, but that does not seem to be true if you add two rotation matrices. Would you get a rotation matrix? No, you would not get a rotation matrix. Now coming to the question of in Euclidean space, if I had two vectors like this, it is easy for me to define the notion of adding two vectors. All that I do is I have to translate this vector parallelly and bring it here, right? And bring it here or along such direction and then add this up, gives me the resultant vector. But it is not very clear how I do this on a circle. Suppose I had a vector here which is maybe describing the velocity of a particle moving in a hoop, right, or a vector here. Now, is there any way I can compare this vector to this vector? It is not very clear. I cannot move this vector like this and bring it like this here, because all this is not included in the circle. The universe for the particle is just a circle. It does not know this exists at all, right. So, how do we talk of these things? All right. So, having defined smooth, so I said there are lots of applications, satellites, rigid bodies in robotics, many others, maybe interconnected rigid bodies. Again, extensions of this when you are not concerned about orientation alone, but you also have translation, right. Now, so let us take, so if you are talking of attitude of a spacecraft, right, then your configuration space, so I will use this word configuration space, it basically means where do the configuration variables of a mechanical system are the basic set of variables that specify the entire configuration, right. If you have a two-link manipulator, you have one angle here, one angle here. So, so this is the rotation matrix. Let's say two-link manipulator, planar. S1 cross S1, right. The first joint is on a circle, the second joint is also on a circle, S1 cross S1. So, that is the geometric notation for configuration space. Now, the question is, say two-link manipulator, you would also like to describe velocities, right. It's not just about configuration, you also want to talk of velocities. So, if you talk of two circles, so this is for the first link, this for the second link, right. So, this is a circle, this is a circle. So, you can think of this as this is describing with reference to some position your theta angle, right, theta 1. The same way here. So, this is with reference to some reference describing theta 2, right. A nicer way of looking at this is you can think of this as emerging from what is called a torus, a ring. So, you are thinking of one of the circles as being swept. So, the one circle is this, which corresponds to one link, the other circle is this radius, this circle, and notice each of them has the complete configuration of a circle, right. Now, if I am at a particular point here and my trajectory, so let us enlarge this picture. So, let us enlarge that picture. So, let us say this was some portion of the torus here. Okay. So, let us say my trajectory, that is my system is evolving like this, right. Now, at a particular point we all know that as a system moves there is something called a velocity vector. So, let us call this point q, this is the velocity at q. Now, I could have been moving through that point in various ways. I could have been going like this, I could have been going like this, and therefore, my velocity vector could have been this way, could have been this way, right, my velocity vector. Now, in this particular case, the velocity vectors, from intuition you gather that it is the tangent surface at q to the torus, right. In that torus at a particular point it is a tangent surface. So, this gives rise to a notion. So, let me now call it tangent space at q to what is called, this is called T2, which is product 2 copies of the circle, right, at q to this, right, all permissible velocity vectors at the point q. Now, how do I get them? I get them in the following sense. So, if I have identified a point q and I draw a smooth curve. So, this curve, what is it? It is it's, let us call it alpha t. Alpha t belongs to the manifold M, right, and we are considering these manifolds as sitting in some ambient Euclidean space, right, and this velocity vector at q is written as where alpha 0 is q. That is, so if t takes some values in some interval minus a to a, the negative is just sort of to keep notation simple. This velocity vector is d alpha by dt at t equals 0. So, you could have many such curves, right, which satisfy this requirement and but give rise to different velocities, right. Now, the set of all such velocities vectors at q, which I will call belongs to an object called TQM, here M was S1 cross S1, forms this set is a vector space. That is, if you generated two velocity vectors VQ1 and VQ2, right, then all linear combinations of that also belong to the space, and all other properties of a vector space. So, this entity is a vector space, if I call a vector space V, right. So, you can add them up the way you do things in Rn, you can do all the operations on Rn. So, please remember, the configuration variables evolve on a manifold. The velocity vectors at a particular point belong to a vector space. So, all velocity vectors at a point belong to a vector space called the tangent space at M. Okay. You can also show certain other properties, that suppose I generate a vector, the linear combination of these, or in this particular case, say in this particular case, it's the associated vector space is R2, which is a plane, right, and I generate some vector in R2, I can also always show that there is a corresponding curve which passes through that point at this 0, and whose velocity vector is that particular value in R2, particular vector in R2. So, in a sense, in this case, so depending on what I forgot to mention that in the morning, that there is a notion called the dimension of the manifold. Right. So, that dimension is, in the case of the first example that we considered, that was one was S1. What do you think was the dimension of this? So, think of it as how many independent variables you required. 2. Was that independent variables? You started with x1, x2, but they had a constraint, x1 squared plus x2 squared minus 1 equals 0. So, you need only 1. So, the dimension was 1. So, in this case O2, how many variables did we start with? 4. And how many constraints did we have? 3. Therefore, the dimension was 1 again. Right? You started with picking 4 variables, but those 4 variables were constrained by 3 equations. So, essentially have a one-dimensional manifold, right. So, similarly, the tangent space at each point of this manifold is the real vector space of one dimension. So is it here, and in the case of SO3 or 3. SO3 is 3-dimensional. So many of you have seen orientations, rotations. How many Euler angles do you use? You use 3, right? Right? When you use quaternions, you have a constraint. How many quaternions do you use? Quaternions come from S3, 3-dimensional sphere. So you have 4 variables to start with, but the 4 variables are constrained by the unit length condition, right? Okay. How many of you are familiar with the notion of a dual of a vector space, dual space? Nobody has heard dual of a vector space? Okay. So I will just have to then say the following or make the following statement. Is so far we have studied smooth manifold, and now I have mentioned what is called the tangent space at a point Q. 2 things I mentioned: tangent space at point Q, allowable velocities, right? Now suppose I associated with every vector space is a dual space, right? A dual vector space, which is basically the vector space of all linear functionals on the manifold. Linear functionals. Linear functionals, clear? Linear functionals, are you clear? You're not clear, okay. All right. So let's take a diversion. So this is a vector space V. You have something called, I'm using, okay, I'll use star. So I'm using star here, I'll explain this later. So this is the dual space. What does the dual space consist of? It consists of all linear functionals right, and by linear functionals what do I mean? Basically F takes, so I'm considering what are called real vector spaces. F takes V to R. It takes an element of the vector space, gives you a real number, but in addition, because it's linear, it has the following properties. X1 and X2 are here, 2 elements of this. Right, they satisfy this. So the set of all these linear functionals also has a vector space structure, and that forms the dual space. So my suggestion to those of you who have not done formal vector spaces, how many of you have done formal vector spaces? I mean at least half of a formal course. I mean even the students from IIT Kanpur, quite a few of you. You have done a formal course. So how come you have not seen dual spaces? You knew it. What about yourself? You are also from IIT Kanpur, but you are not. Okay. Anybody else? I strongly encourage you to go. I don't know whether on YouTube, Nidhish, on YouTube, are there any formal vector space courses? None at all. But I think Strang's lectures introduce you to dual space, I think, right? No? Gilbert Strang?
So he does, but not very common. It does not cover the dual space.
He doesn't mention the word dual space?
No.
Linear functions, okay.
He tells all.
Yeah, the reason I'm saying this is a lot of advanced engineering is based on these basic notions. If you know these, you are able to sort of move forward more quickly. Though they are abstract, they give you a lot of sense when you're looking at functions, functionals which are functions of functions, and things like that.
Even vector space many people do not cover.
Yeah, because it's something I would encourage you to please go and study from whichever source. I can give you a few texts, but I think you have to work through problems to understand this. Okay, so this is the meaning of a dual space. I'm sorry I won't be able to go more into that. So dual to the tangent space is a vector space called the cotangent space. And why do we need the cotangent space? Because all the forces sit in this space. In a mechanical system, what are the variables you are usually interested in? Configuration, velocity, acceleration, forces or torques, right? So forces and torques sit here, velocities sit here. We will describe where accelerations sit. I mean, so the other object that you need is, if you sum up over all m, not sum up, take the union over all m, all points you union. So you have an entity called the tangent bundle. And similarly, if you sum up over all m, tangent bundle. So Nidhish, as the last thing, should I cover the Lie derivative and Lie bracket before you take over, or what's your suggestion? It's 12:20, so you have about 55 minutes now. Okay, so what do I cover now? Do I cover something now or do that later? Okay. So yesterday in the process of doing all Lyapunov theory, we studied something called vector fields. We talked of the drift vector field, control vector field, right? So you often, suppose you were looking at some neighborhood in Rn, right, and you had a function defined on this neighborhood, right, f, which takes you to R, some scalar function. Think of it as in your harmonic oscillator, think of it as energy is a function, right? It gives you a real number for, right? Now, suppose a vector field is specified. So, you have a vector field on the system and we ask the question, what is df by dt? How is the quantity f? So, let us make a few things clear. So, x dot equals, okay, I should not use f for this. Let us call this function h, okay, and this is f of x. So, this is a scalar function, this is your vector field. So, h is a function of x, the variables of the system. So, if I am asked what is dh by dt, do x dot fx, right. So, this is also called as the Lie derivative of h along the vector field f. This is Lie derivative. This notion, which describes the rate at which a function of the variables, state variables changes. So, to define this, you need a vector field, which is what here. This is nothing. So, this bracket is just the inner product of this, or the dot product is called the Lie derivative of h along f, right. So, if you looked at your system yesterday, the simple harmonic oscillator, you had if you defined an energy function which was k x1 squared plus half m x2 squared. Now, you could evaluate alongs the vector field f e. What will you get when you do that? I do not have the vector field right now, but we wrote down the system yesterday. So, can you check what you will get?